Is the plan. Today we're going to talk about QuickSort, which you already started a little bit. This is completely an honest thing. Even in the algorithms class that you're going to have later, you're not going to do the full QuickSort. The full QuickSort happens at the master level. But we're going to do enough to what we can do today. In particular, we're going to focus on the recurrence, the math part of the recurrence, not so much the QuickSort implementation. We have to start graphs because you guys have a homework that's with graphs. So that's a problem, right? We're not going to do all the graphs required for homework 10. So there will be at least one problem in homework 10, the one with the problem 3, I think, which is easy. But for that, you're going to need something that's coming on Tuesday. So just a fair warning, you can do a lot of the homework starting today, but not one or two problems. You're going to have to do those. Yeah. Homework 10 is due, a week from Tuesday. So those problems that I'm going to do Tuesday in class, if you happen to miss the class on Tuesday due to Thanksgiving, I understand. We'll make sure we record the class, and you have to see that and read the slides or the notes so that you can do everything that's graph algorithms, traversals. That's not going to happen today. That's going to be on Tuesday. Then next week, there's nothing other than the class on Tuesday. The week after that, we have the last class and the homework due on Tuesday. And then on Friday, you have to be done with the honors problems. That includes all the demos, including the demo for problem 5, which you haven't seen yet. That's going to happen today. Today we're going to talk about this problem number 5 for honors, which is due 2 weeks from today. And then we have an exam review session that's purely, I skipped something here, right? There's something 12, 4 optional recitation. So that's a start problem. The optional recitation is nothing to do with the material and the exam and the grades, so you come there if you want to see some interesting math problems. But this exam review session is exactly the opposite. It's only regular material that's relevant for the final exam. And then Tuesday, I think, is the 10th, is the final exam. That's the plan. So let's start. My plan is to split today into 3 parts. Finish QuickSort, which as I see today, it's purely analysis, recurrence type of thing. Then we have to do graphs, the intro part, which most of you have seen, and we've done it a little bit at the beginning of the term. It's a very simple stuff. It's nothing intellectually challenging in the graphs, because we get definitions. But then we have to look at these skip lists. So let's start with QuickSort. Maybe starting here. QuickSort is we already put QuickSort on the board, right? We have an array. Here's the array, and we want to sort it. So say array from the beginning to the end. We want to sort this array. There is a there's a function that applies to this A. It works like magic. And I mentioned it before. And because it's magic, we're going to leave it as exercise. This is nothing to do with the sorting or with the QuickSort recursion. So it's like in merge sort, it's an auxiliary function that does something very specific. What this does, it transforms the array A into, it makes a modification of the array. So now after the partition, I have an array, the same array A, where I have this pivot index, and the value at that pivot is in final position, final sorting position. So this function puts a value somewhere in the array that doesn't have to be moved. Okay? That means this value will be there in the sorted version of the array. So I don't have to worry about this value after this step. That's the idea. So in here, all the values will be, say, call this A of P. All the values here are going to be smaller than the value, and all the values here are going to be bigger than the value. So partition does really two things. It puts a pivot at the pivot index a value that's one of the values of the array. And then it takes all the values smaller than that, moves them on the left side, and all the values bigger than that on the right side. But the sides are not sorted. So as an example, here's how that might look like after partition. I don't have one here, so I'll have to make it up. So here's my array. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the indexes, right? Maybe somewhere in here I have my pivot. So in this position I have a value 12.5. What that means is, this is one of the values of the array, but now all the values smaller than 12.5 are on this side, right? So this might be a 3, this might be a 9, and this might be a 4.2. And all the values bigger than 12.5 are on the right side. So let's say this is a 17, 19.5, 100, 20, 25.3, and say 14. After partition, here's my P, right? P is 4, and A of P is 12.5. And this is the left side, that's all smaller than 12.5. And this is the right side, that's all bigger than 12.5. That's this utility function partition. This is not a recursive call. This is like in merge sort, the interleaving procedure was not part of the recursion. It just takes what you have, combines them together. Now, as opposed to merge sort, in QuickSort, this happens before the recursion. In merge sort, if you remember, the merging interleaving procedure happened after the recursion. Once I sort the left side and the right side, I did merging to combine the two together. Everybody remembers that in merge sort? This happens before the recursive call in QuickSort. So this goes first. Now your exercise, which I already posted but I think nobody did, is to implement this function. If I give you an array, figure out how to put one value of the array, you pick one at random, 12.5, somewhere, such that on the left side you have the smaller values and on the right side you have the bigger values. Do you think you could implement a function like this? Pick a value, figure out where that value should be in the array, what spot. If it's like the fourth, this is the fourth value, so it should be in position 4, right? In sorted order. And then, how do we move the small values to the left and the big values to the right? And how long would that take? How long do you think it takes? If you are to implement this function for an array, find the value, the pivot, move the left ones there, but you don't care about the order. This guy's moved in here, could be in any order. You think this is going to take linear time? Let's see. We want to see that program that does this in linear time, okay? And the pivot is unspecified. Ideally, of course, we would like this P to be in the middle, but we're not worried about that. You find the P, the partition doesn't specify that the value should be somewhere in the middle. It could be somewhere like very close to this end or very close to that end. Any pivot counts as a valid pivot. Right? The critical part is to have that value in the right spot. So once I'm done with partition, if the pivot is 4, the value at 4 has to be the 4th value in the array. Exactly from the, smallest values be the 4th one, right? 1, 2, 3, 4. And move the left side and the right side. So that's my partition function, which I think would be a good exercise to implement. Also, this is in place. We don't want this function to use auxiliary arrays. So that's another wrinkle to it. When you implement this function, you have that array. You can do anything you want with it. You can totally destroy that array if you want. But you don't want to use another array like auxiliary, data to do your job. So a difficulty for partition is that we want to move stuff inside the array without using some matrix data structure or tree or hash. That's in place. And then once I have that, how can I proceed into sorting? Suppose this is already given. I've done the partition. Remember, that's not a recursive call. It's just an auxiliary procedure. I've got my pivot, P. I've got the value there settled. I don't have to worry about that value because in the final sorted order, this value is going to remain right here in position 4. Right? All I have to do now is worry about sorting the left side and sorting the right side. Because once this is sorted, they're all smaller than this, and once those are sorted bigger than that, everything will be sorted, right? Hands up who follows that. So now what should I do here? This is easy. Once I organize my array this way, how do I proceed here recursively? What do I do? Yes?
You call QuickSort on the left side, and you call QuickSort on the right side.
What exactly is the left side?
From B to partition value.
P minus 1?
Yeah.
Because P is the pivot, that's already done. I don't have to sort that one. So I'm sorting, that's sorting the left side. And then?
QuickSort from P to
I can sort the right side. Simple, right? that should be easy to understand if you, by now you're familiar with recursions. Once I'm in this position, all I have to do is sort left, right, and right side to get the whole thing sorted, because already the smaller values are on the left side and the bigger values are on the right side. And this, it's not dependent on each other. I could do this in parallel on 2 computers. I don't have to wait to the right side for the left side to be sorted or anything like that, because they're independent processes now. One can take over that part of the array and do it, the other take over the other part and do it. It doesn't matter who finished first or what computer is faster, nothing like this. Everybody can see that this is a sorting algorithm. I think it's easy to see that at the end, this whole thing will be sorted. Good. So I think once you implement partition, implementing QuickSort should be very, very easy, right? The difficult part implementation-wise here is the partition function. Calling recursively the QuickSort on half of the array, it's very simple. It's over there, half a line code. This is the tricky part, which is now, we're now going to talk about this today. I'm happy to discuss it with you, some office hours or separately, and there's plenty of notes about this. But this is not my interest for right now. In your algorithms course, you're going to spend a lot of time on how this partition function works. For now, what I want to do is analyze the runtime. So if I look at this P, and I want to do the same thing that I've done for merge sort or insertion sort, or actually for recursive calls, merge sort. I want to say D of n is really D of left side plus D of right side plus n. N is from the partition function. That's how we analyze a lot of algorithms that are recursive. We said if you want to look at the runtime of QuickSort, you do the n, that's the partition steps, and then you have to do the left side, right side. Since t is the runtime, it be t of the left to be how much time it takes to do the left. Now, in principle, that would be something like T of P plus T of n minus P. I'm skipping the plus 1 minus 1s. Plus n. Right. This, it's unusual as a recurrence because it really depends on this P thing. The recurrences we've seen before were on n, like merge sort, it didn't have the P in it. It has T of n by 2 plus T of n by 2 plus n. If I could guarantee somehow that the pivot is in the middle, I would have exactly the same recursion as merge sort, right? Half, half, and n. So that I know how to solve. The problem in QuickSort is that I don't know where the pivot is. I can't control that. So what we're going to do here, we're going to say, what are the options for this P, right? The left and the right have a bunch of options. I could have n minus 1 and 0, n minus 2 and 1, all the way to 0 and n minus 1, right? Sizes. Again, partition will not be able to promise where the pivot is. That will be very nice to be able to guarantee somehow the pivot is in the middle, but we can't, to have it in linear time. So then we don't know the pivot is, and we're wondering, okay, what are the options for this split? Well, it could be maybe half and half, maybe more on the left, less on the right, so on and so forth. Anybody wants to make a guess? What's the worst case? Yes. No, not the runtime. What's the worst case for the split? If yeah, P is at the extreme. Either 0 or n minus 1. Always. Remember, the pivoting thing happened recursively multiple times. It happened once, then I move to the left side, right side. Move again, move again. So this partition will happen again once I recurse into the left side that has another partition in it, right? So worst case, P is at the extreme. And what's to be the recurrence in that case, roughly? T of n will be T of 1 plus T of n minus 1 plus n, approximately. I'm skipping the plus 1 minus 1s in here. If that's my recursion, what the runtime will be here? This is definitely n squared. So that's the kind of recursion you can easily have in a final exam. Here's the recursion, solve it. Asymptotically, which means it's n squared. A recursion that works like this, T of n, it's a constant. T of 1 is a constant. It could be some value p in there, right? Constant plus T of n minus 1 plus n. That is an n squared recursion. If you're not sure, you should solve this problem. Okay? What is the average case though? That is my interest for today. Assuming somebody is not my hidden adversary somehow and makes my splits always with these pivots at the extremes. Like somehow somebody is playing with my input in my program so that I always get extreme splits. I'm gonna assume that the probability of each split is roughly uniform. There's n possible splits, right? And I'm going to say, let's assume I'm not in an adversarial case where somebody is on purpose making my algorithm look bad, like find a way to always get the split bad. I'm going to assume I could get good splits or bad splits. These are all the possible splits, right? The pivot could be one of these positions. Let's assume the chance of the pivot being one of those is uniform. And I actually think I have a way to do that in a partition. When you implement the partition, can I enforce uniformity by picking a random value to be my pivot? Suppose I get an array. I pick a value at random to be the value of the pivot. So I could have picked 9, 3, 4.2, 12.5, 17, 19, 100. I could pick any one of them at random. would that mean the split will be uniformly over the possible splits? All I have to do in this partition is when I implement it, pick the value that I want to be my pivot value, not the index, the value. Pick it at random from the array. So look at my array, it says pick one at random, that's the pivot of it, that's the value of the pivot. I think if I pick that at random in the beginning of partition, decided very early on, randomly, which value is, could have been 19.5, could have been 20, could have been 100. I pick that at random, I think I have a uniform chance to all splits. So what would be again the extreme cases? What would I pick as a very unlikely value for the split here? What would be my very extreme pivots? If I pick the 3, that's extreme, right? Which one is there also extreme? 100, right? And if I'm very lucky, maybe 17 or 19, I don't know, or somewhere in the middle. But picking at random, I think, effectively enforces this to be a uniform split. So I'll try to do that in all my partitions. Pick the value of the pivot at random. Okay? What about the average case? I'm going to use averaging over all possible cases. Averaging of all possible splits. Uniform. So then I think I get D of n is 1 over n, sum from p equals 0 to n minus 1, T of p plus T of n minus p minus 1. Let's include the n in here to make it clear what it is. So what I'm saying is, for every possible pivot, you get this sort of split. I should have right here. Do not get lost. For every possible pivot, you get a split. Now I'm averaging this 1 over n. It says take an average over all possible splits. This n is the same n everywhere. But the p versus n minus p minus 1, it changes. From p equals 0, I get t of 0 plus t of n minus 1. On the other end, when p is n minus 1, I get n minus 1 and 0.
Why not just find the expected value of p and then just plug that into your insertion? So it should be roughly a number 2. And then just
Right, so he is asking a hidden question here. What he's saying is, you want the expected value of the runtime for QuickSort, right? Why not measure the runtime of the expected value of QuickSort given the pivot? So he's saying, instead of expectation, what's what I want average of the all possible runtimes, he's saying if you can measure the expectation of the pivot inside the QuickSort and then the runtime of that, that'd be easy. Right? I don't know. Does the same thing or not? That requires some proof, right? Yeah. That's a very good statistical question. When the expectation distributes over the function, in this case runtime, that you want to compute, is it the runtime of the average pivot the same as the average of all pivots? I don't know. I can come up with an example where this is not true. If you paid attention to some problem with infinite returns in the recitation, there was some problem with an infinite return. I think those kind of cases, one value will be infinite, the other one will be finite, for example. So this needs a proof before you can proceed with that sort of thing. So, okay, what am I going to do here? Let's call this one somehow. I think this is, I'm going to call it 2 to the n So what is this? What I have here is 2 to the n. Let me write the n first. This n, it's n of them, and then it gets averaged by n. It's just an n, plus 2 to the n sum from k equal 1. I say p, right? P equal 1 to n minus 1 of t of p. Where is the 2 coming from? Somebody else. How come? Everybody can see what happens to this n. N plus n plus n plus n plus n so many times, divide by n. That resulted in this n outside the sum. That's easy. But then these t of p's are coming from inside, but instead of a sum of 2, I only have 1, and I got the 2 here. How did that happen? Yes.
The TP and Tn minus p minus 1 is sort of symmetric, so as you increase n, it's the
Right.
same.
Everybody t of 3 has been counted twice. One was counted for 3, a t of 3 plus something, and the second time when I got to n minus 4 or n minus 3, there was a t of p on the other side, t of 3. So every t of p was being counted on the left and on the right. That's why there's 2's of each one of them. Good. So now starts the grinding. Who is t of n minus 1 then? I can, that's true for any n, so I take that formula and I plug in it n minus 1, I get this. Now I'm taking that formula there, t of n is n plus 2 divided by n, sum of p equal 1 minus 1 t of p. But I want to multiply this. I want to multiply this with n. So this is, if I multiply with n, I get n t of n, it's n squared. Right? N goes away in here. So from this one, let's put a star to it. And I'm going to say here, this is the equation star multiplied times n. I took that one and I multiply with that. And now I want to do a difference here. Actually, let me write this in a way so you guys can follow. N t of n by n. I'm going to write it here, multiply. N t of n is n squared plus 2 sum of t of 1 equals n t of p. And now this one, I'm going to multiply. So here I multiply by n. This one I multiply by n minus 1. I get n minus 1 squared t of n minus 1 times n minus 1. It's n minus 1 squared plus 2 sum of p equal 1 to n minus 2 t of p. And now I subtract those two things. N t of n minus n minus 1 t of n minus 1 is how much is n squared minus n minus 1 squared? This minus this. Let's leave it like that for now. More importantly, those sums have a lot of the same terms in them, right? When I subtract from this sum, I subtract this sum. The 2 is the 2, so that's good. But what is left from the sum? This is from p equal 1 to n minus 1. This is from p equal 1 to n minus 2. So this sum, I'm subtracting from this to this minus that. So what's left in here, a lot of things go away, but what's left? T of n minus 2. Okay, so let's compute this difference here. Everybody knows the formula n minus 1 squared, n squared plus 1 minus 2n. So when I do the difference, I'm left to 2n minus 1. That difference comes in here. Plus 2 t of n minus 1. So now I have n t of n equal n minus 1 t of n minus 1 plus 2 t of n minus 1 plus 2n minus 1. That is n t of n. I see this and this being the same orange here. That's n plus 1 t of n minus 1 plus 2n minus 1. And if I want, I can divide this with n to get n plus 1 over n t of n minus 1 plus 2 minus 1 over n. I haven't solved the recurrence yet, but I think this looks prettier than I started with, an average over all possible splits of the pivot. So there's a lot of straightforward arithmetics here, but this idea, multiply this with something and this with something, we've seen this idea before when we did our first take on 1 plus 2 plus 3 plus to the n was to multiply or rearrange it, subtract it, to do something like this. How did I come up with this idea? What's my drive here? To come up with multiply this with n minus 1, multiply this with n, and do a subtraction between the two. How did I come up with such a thing? Yes.
You want to get rid of the p's, so you just...
Which piece?
Like the p, you want to get rid of the sums.
I want to get rid of a lot of terms in the sums. So I'm looking here, how can I get rid of them?
You have to multiply by the denominator.
The problem is one is divided by n minus 1 and the other one is divided by n. So I need to get rid of this n minus 1 and n from the terms in the sum so I can be able to reduce them one with another, right? Because like that, t of 5 will be divided by n minus 1 and this t of 5 will be divided by n. I can't subtract, they won't go away. So I do whatever I need to do so the sums, massive parts of the sums go away. It's a useful trick to know how to manipulate sums. It's not mathematical, it's creativity, right? You have to, of course it comes with experience, but it's not, I can tell you it's a math technique to do so. Just you look at the sums, want to get rid of those, how do you do that? That's what I've done, right? And then the rest is just simple calculations. Now, how do I solve this recurrence? Right? I mean, I still have to solve this recurrence here. Can I do that? Where should we put it? Maybe here. If I ignore this, I'm going to get t of n smaller than n plus 1 by n, t of n minus 1 plus 2. I'm ignoring the minus 1 over n pi. That's why instead of equal, I get smaller than equal values. You know, I can say, I'm going to ignore this for now. Because it's, you see, the way you can ignore these terms is that in a recurrence, like this, I have some recursive part, this one here, and some constant. That in all recurrences, you have some constant that doesn't depend on n, perhaps, plus 1, plus 2, plus 7, something like that. This 1 over n wouldn't change the fact that this is a constant, right? The fact that this is 2 or 2.1 or 2.3 or 2 point something, eventually when n is large, 1 over n is a very insignificant amount that can be just included in that constant, right? I can say this is between 2 and 1.99, roughly. So it's kind of like, for all practical purposes, still a constant. As n goes big, 1 over n doesn't affect this particle. That's why I can get rid of it. So how do we do this? Let's move the 2 here, 2 plus. Let's do iterations, right? Isn't that what we've been doing? 2 plus n plus 1 over n. I'm expanding this guy now. What do I get? I'm using the same recurrence, just not in n minus 1. So what is it going to be? Remember what we did last time? We keep expanding until we figure out the pattern. Well, what's the pattern? 2 plus t of? Okay. Well, let's do some cleaning. Remember, when you do iterations, you want to do a cleaning before you move to the next iteration so that it looks nicer. So what do we get there? 2 plus 2 n plus 1 divided by n, right? Plus, oh, here's something nice. What happened here? N plus 1, n minus 1. How much is this? This fraction, when I multiply these guys with these guys, I get what? N plus 1 divided by n minus 1. I still have a t of n minus 2 in there, right? Okay. Well, let's keep going with it. So 2 plus 2 n plus 1 divided by n plus n plus 1 divided by n minus 1. Now I'm expanding the 2 of n minus 2. So I'm putting my square brackets because I want to see exactly who's expanded when I look at this thing. What goes in there? 2 plus, I'm applying the same recurrence, but now my inside argument of the recurrence is n minus 2, right? So what do I get? N minus 1 over n minus 2, like that. T of? Like that? So how much is this cleaning part? 2 plus 2 n plus 1 over n plus 2 n plus 1 n minus 1 plus, how is this going to work out? N plus 1 divided by n minus 1 times n minus 1 divided by n minus 2, how much is that? N plus 1 divided by n minus 2, t of n minus 3. Let's do it one more time. 2 plus 2 n plus 1 divided by n plus 2 n plus 1 divided by n minus 1 plus n plus 1 divided by n minus 2, square brackets, expansion here. What do I get here? Now I'm expanding t of n minus 3, right? Is what? 2 plus n minus, how much I've got there? N minus 2, right? Divided by n minus 3, t of n minus 4. Right, cleaning. 2 plus 2 n plus 1 by n plus 2 n plus 1 by n minus 1 plus 2 n plus 1 by n minus 2 plus, now I have the same two fractions multiplied with each other. I'm going to get n plus 1 divided by n minus 3 t of n minus 4. What's the general pattern here? Or do we need to do more, or can we state the general pattern? So general after k iterations. So this was k equal 4, this is k equal 3, this is k equal 2. Can somebody tell me what is this going to be after, generally speaking, k iterations. Looking at these patterns, and I try to figure out which pattern is the one, the general formula. Yes.
It's 2 times the quantity times, or 2 times n plus 1 times the harmonic sum from 1 to n plus 1 minus the harmonic sum from 1 to n k plus.
So you say 2 times n plus 1, like that?
Yeah.
Times the sum here from,
Yeah.
for k, it's I equals 0 to
n plus 1.
k, because I'm in the k. K is the,
But I was going to do the sum up to n plus 1, and then minus the sum from I equals 0 to k.
let's just do something so we can see the pattern here. Perhaps it would be easier to write it without the sum first so everybody can see it. This is 2 times 1 plus 1 over n plus 1 over n minus 1 plus 1 over n minus 2 plus what is the last thing that's being divided with in here? Not the recurrence part, this one. As with respect to k. If k is 4, this is n minus 2. If k is 3, this is n minus 1. So what do I have there? 1 over n minus k plus 2, I think. The last term, that is 2 times something, n plus 1 move to the front. But this, you can see, this is n minus 2 for k equal 4, n minus 1 for k equal 3, and n for k equal 2. So if I do n minus k, that would be in this case n minus 4. I need to add 2 to it to fix that last term. So that's that, plus n plus 1 divided by, how much is this n minus 3 with respect to k? Minus k plus 1 times t of n minus k. So that is going to be,
Your first term inside is 1 over n plus 2.
this is 1 over n plus 1?
Yeah.
Correct, because it's 2, so I need n plus 1 divided by n plus 1 to get that 2. So the general, I can write it as a sum, 2 times n plus 1 now, sum from k equal, what do I have here? 0, I, not k, I equals 0 to n minus 2, 1 over n plus 1 minus I, that's the sum, plus n plus 1 divided by n minus k plus 1, p of n minus k. So just like before, when we figure out, we solved recurrences last time, what is the last k? I need the interior here to be, say, t of 1. I want n minus k to be about 1. That means k has to be about, once we figure out the pattern, we have to decide when this is going to stop. This is true for every k, k equal 1, 2, 3, 4, 5. Up to what's the maximum k this is going to go. That's where the interior of t becomes a constant, 0 or 1. Right. All recurrences will be stopped that way. Once I have the pattern, what k do I need to determine the base case? So that will be k is roughly n minus 1. And if I plug this in there, I get 2 times n plus 1, sum from I equal 0 to n minus 2 of 1 over, this is not n minus 2, this is k minus 1 over 1 over n plus 1 is I plus n plus 1 divided by 2. So while I think the exact mathematics here, the exact arithmetics, you can take more time to think about it at home. That's the easy part. If you get scared about these sums, That's not that hard. What you have to understand is that this principle here is the same like recurrences we did last time. We find a pattern by few iterations. We decided what's the general pattern. So this is an absolute critical step. The general pattern is this for any k. Or that. This is the same as that, just written in some notation. And now I figure out what's my base case. How do I get the interior of this t to be 1 or 0 or 2, whatever my base case is. Let's say 1. It won't matter what we put in there now. So if we want n minus k to be 1, k has to be roughly n minus 1, right? So then I replace that k in. Since it works for any k, I can put that k in. I put that k in, and I'm getting this sum here. Now, this is just a harmonic series. Just is written backwards, but it's really a harmonic series. You can see it in here. It's going to be a harmonic series, not starting from 1, but starting from 1. What is the, this in here, if we were to write it, would be 2 times n plus 1, that's the front. What is exactly the terms that happen in here? The first one is 1 over n plus 1. What's the last term? It's not 1 over 1 like in a harmonic series. When I equal n minus 2, what do I get here? This is n plus 1 minus I. So to be a harmonic series, it will be all the way up to 1 over 1, but this doesn't go all the way there. The last term is how much? N plus 1 minus n minus 2, how much is that? 3. Plus n plus 1 by 2. This doesn't matter that it goes to 1 or 2 or 3. Asymptotically, this thing is still same like the harmonic of n. The fact that it's missing the first 2 terms, which is 1 over 1 plus 1 over 2, right? Everybody remembers who harmonic is? 1 over 1 plus 1 over 2. Harmonic series, it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over n. This is harmonic of n plus 1, except it's missing the first 2 terms in there, right? The first 2 terms are a constant, so it don't matter for the asymptote, right? Hands up, please. I've got like harmonic series, but I'm missing the first 2 terms. I cannot call that harmonic series, but asymptotically, it grows like a harmonic series. It's only missing the first 2 terms, which are really 1.5, right? 1 plus 1 over 2, it's 1.5. So asymptotically, they're the same. So by the way, what's the asymptote of the harmonic series? Didn't we do that 2 lectures ago?
Log n.
Remember when I showed you that the asymptotic series is pretty much like the logarithm was pretty tight in there? So now if this is the like log n, I'm looking at 2n plus 1 times log n plus n plus 1 times a constant. T of 1, it's a constant. I don't know what it is, but it's a constant. How much is this going to be? N plus 1 times asymptotic of log n plus n plus 1 times a constant. The asymptote is going to be n log n, because n times log n is n log n. And this is a linear term that's smaller than n log n. We're done. Okay, so what have we done? We look at the quicksort and we say, if we are not always unlucky somehow, if we can assume that in the partition, the pivot doesn't always come at the extremes. There is a uniform chance of the pivot being any one of the values of the indexes of the array, right? So the splits could be all the possible splits with probability uniform 1 over n. We took the recurrence and say, okay, well, this is the recurrence for a p, but we average over all possible p's. And then we average that recurrence down to here, and then we solve this recurrence with iteration method, and we've got n log n. I would call this clean enough that we don't need an induction proof. Remember what I told you last time? If this derivation here is clear, like in here, this is clearly the harmonic series that we know. But sometimes imagine you get something with like squares. And you're like, I don't know what that is. But I'm guessing it's that. You can make a guess and then do a different proof by induction. When this is clear enough like this, I think we can leave it like that and say, look, this is log n times n. Let me write it one more time. This is n plus 1 times log n plus this is O of n, because it's linear. So that is really n log n. So what we did overall is to show that QuickSort, on average, takes n log n time, asymptotically. That's still possible that QuickSort can be in one run unlucky and take n squared time, right? We have it here that if your splits are always breaking like extreme, extreme, extreme all the time, the actual runtime will be n squared. So it is possible to get some cases n squared, but on average, it's going to be n log n. In practice, QuickSort is the most implemented and used sorting method, except when the data allow us to make some assumption to do it linearly. Remember bucket sort? Anybody heard of counting sort? There's a bunch of other methods that work in linear time, but they require heavy assumptions about the data or the range of the distribution or something like that. So QuickSort is used in practice a lot when we cannot make any assumption of the data. We know it's an array, we don't know what's in it, we need a sorting method that works all the time, fast. It's typically QuickSort. You could ask, why not merge sort? Merge sort works all the time, and it doesn't have this problem, right? Merge sort is never n squared. It's always n log n because it always splits in half. And it works all the time. Merge sort doesn't make assumptions. Yet QuickSort is the one that's being used all the time. When you call sort in C++, you get the QuickSort. So I have that question for you. Why is QuickSort used and not merge sort? But before we get to that, there are faster methods. Linear time, radix sort, bucket sort, counting sort. If you can know something about the distribution of the values, or the range, like I'm sorting by age, and the age is between 0 and 150, not more than that, then you can do faster methods than n log n. But in general, if you don't know anything about your values, n log n is the best you can do, right? And so, why is it that QuickSort is being used and not merge sort? Yes.
Merge sort requires you copy the whole array multiple times for every iteration.
Yeah, I do what? Requires what?
You copy the whole array.
Right. This. QuickSort, all it does, it works in the array that you give it to it. It doesn't need additional memory. It doesn't need additional copying. Merge sort spends a lot of time combining those arrays into a new one, producing that new one for the output, so on and so forth. That's too much lagging and memory usage in there for practical purposes. So that's what's being used a lot. A lot of these will be part of your algorithms course. So that's merge sort. So you've seen a definitely honors level recursion. This one. There'll be notes online, and there's a faster way to do this with more tricks. So there's a cleaner way with some arithmetic tricks that require creativity. If you can see it creatively, as in the notes, you can skip this whole thing. But I wanted to show you like that because that's what's going to happen in most recurrences that you solve. You're going to have to iterate until you find a pattern, and you have to be smart about this. Looks like harmonic series for me. So I'm kind of modeling with harmonic series. I have to know the harmonic series approximation. Many of these will be geometric series. The ones that we did last time with master theorem. If you don't use master theorem, you end up with a geometric series in here. So you have to know your series to be able to calculate the values. All right. So what we're going to do now is to talk about graphs. Let's maybe do it here. A lot of the things with graphs you already know, so I'm going to go as fast as I can here. Bunch of notes. What do we have? Graphs. Let's make kind of a table of contents, because I think I think most people heard of all those things, but just to kind of give it all in one table. We have, of course, edges. These are the E sets. So a graph is usually V and E sets, and E is a subset of V times V. In other words, U, V are vertices, and UV as a pair is an edge. So you have something like for example, these are vertices A, B, C, D, E, F. So V here will be A, B, C, D, E, F, and edges will be things like A, C, A, D. Those are pairs. No A, B, B, C, A, D, D, F, G, F, D, E. I think everybody's seen a drawing of a graph before. There's many, it's enormous numbers of applications of graph in terms of modeling. This could be cities with roads between them, could be airports with flights between them, could be water reservoirs with water pipes between them, could be routers in a network with bandwidth associated with how much information can flow from one router to each other. Could be your courses, here's CS1800, here's other course, what's required to take what other course. Could be Facebook graph where these are friends, here's a person and here are his friends on Facebook. Could be web pages, that's a link between them, right? The web link, like from this page I can get to that page. A lot of problems can be modeled. Could be actors, and the edges be those two actors appear in movies together or not. A lot of these could be modeled like graph, which involves some entities and some connections between them. Graph theory is its own field of study now. It's kind of brought from mathematics into graph theory. That's the mathematical side of things. And then there's a computer side of things, how do you implement all this? How do you solve problems using graphs? Okay, so we have vertices and edges. We have simple, which we only gonna call graph. Every time I say graph, I mean a simple one, versus not simple. Not simple might mean something like there's two edges between those nodes. That's not simple. We usually, when we say graph or simple graph, we don't allow multiple edges between two nodes. But if you really want to do that, you can. You just have to explain there is a possibility that between two nodes I have multiple edges. Some people call it multi-graph or something. I don't know. If I say graph, I did not duplicate edges, but it could be. Also, they're not loops. An edge cannot be from end to A unless I specify that there is possible to do that, right? So this is a multi-edge. This is a loop edge. Many books, many people use different notations and names. Some people may not call it loops. But my point is, if somebody says simple graph or just a graph, those things are not possible. Then I have undirected, edges, versus directed. Those here are undirected. If I have undirected, like in this graph, what it means is AC, which is the same like AC, like that. Whether you see the edge AC or you see the pair AC, that means the same thing. It's the edge from A to C. It's the same as the pair CA. So if you think of this as a pipe, it means water can flow from here to here or from here to here. It's a pipe. If it's a road between New York and Boston, I can go on that road from New York to Boston or from Boston to New York. If it's a friendship on Facebook, it's reciprocal. C is friend with A is friend with C. But there are graphs that are directed. Here's a directed one. The HAC is not the same as HCA. Here's one I have here. Remember the ones with the Markov chains that we did? We kind of saw a graph in there. There were like things like that. And here's a self-loop here. That's a directed one. In directed graphs, if those are roads, it means I can only go from A to B, not from B to A. I need another edge. See, in here, I have an edge from A to D and a separate edge from D to A. This is not a multi-edge. It's the fact that there is a road this way and a road that way. It's totally fine to have two edges, one A to D, the other one D to A. It will be a multi-edge if I have two edges from D to A. But just having both directions, it doesn't mean it's a multi-graph. This is still a simple graph. Okay? And you have to think really about what you're modeling with this graph. If it's friendship, that would mean I'm friends with her, but she's not friends with me. So that's not a reciprocal graph anymore. An edge doesn't mean immediate reciprocity. If it's, again, I said roads. If it's are web links directed or undirected, those are web pages, and the edges are links between them. The HTTP links are directed or undirected? Directed. The fact that my page points to that page doesn't mean that page points back to my page, right? So in a lot of problems, especially ordering problems, you want to be using directed graphs because things that happen one way does not necessarily happen the other way. What else do we have? We have path. Sequence of edges on incident vertices. So in this one here, I have a path. It's like I have to go from A, say, A, I can go to D. From D, I can go to F. From F, I can go to B. And from B, I can go to C. That's a path. A, D, F, B, C. I go from somewhere to somewhere. I follow a sequence of edges, but I have to be incident. If my last edge was in D, the next edge has to start from D. I can't jump around. Now, in a directed graph, a path has to follow edges in direction. So in here, I can start from A, I can go to D, and then to C, and then to B, right? A, B, C, B. But can I go from B to A to D? Is that okay to go from B to A to D? No, because you can't go from B to A. When an edge is directed, the only thing you can do with it is in the direction of the edge. It's like the edge does not exist the other way. So you can't go from B to A in a directed graph if there is an edge from A to B. In an undirected graph, you can go both ways. But in a directed graph, you have to follow respect the edge direction for anything you do. Those are could be pipes, friendships, bandwidth, whatever, shipping, it doesn't matter. You have to respect the edge direction. So this is not correct. So a path is a sequence of edges, is from a vertex I start the path here, I end here, and I follow edges without jumping around. And a cycle is a path from vertex V, some vertex V, that goes to some other vertices and ends up back in V. So path to same vertices. Same vertice. Now, like with the general graph, I can have simple path and cycles. That's typically when I say path or cycle, I mean simple ones. Or I can have not simple. Repeat in the same path, vertices, or edges. I could say, here's the path. A goes to B, goes to F, goes to E, then back to F, then back to E, then back to F, then back to E. That's technically it's a path because I'm not jumping around. I'm just moving on the same edge, or I can repeat, you know, F D E F D E F D E, and at some point stop in D and move to A. When I say simple path or cycle, I mean you can repeat the edges or vertices on that path. It's something like A to D to F to B. That is not repeating vertices and edges on the path. And now I have degree of a vertex is the number of incident edges in D. So in the undirected case, there's no doubt what that means, right? Here's the edges. I count how many there are. What's the degree here? In this example. 5. What's the degree of this D here? 3. It's simple graph. We draw extra edges just for the purpose of, it's a simple graph, so the degree is 3, right? What's the degree of this B here? 2. 2, so on and so forth. How many edges are in there? Now, in a directed graph, I may have 2 incoming edges, or 3, and 2 outgoing edges. Because remember, in directed graph, edges have a direction. It's possible that some incoming and outgoing is with the same node. If I say degree, what's the degree here? The degree is still 5. If I say in degree, number of edges coming in, that is 3. Out degree, that is 2. Of course, those are all definitions and notations. So if somebody really wants to call the degree just the out degree, you can say that, and then let's call it the pineapple, right? We can call it anything we want. This is just a definition. But I don't care about the exact naming. I want you to make a distinction between in degree, out degree, if the graph is directed. So we talk about cycles. We have a concept of when we did path, we can ask here the question of reachability. So can I reach a vertex B from vertex A? That's essentially asking, is there a path from A to B? Can I start in A, move in the graph, and get to B? All right, what else do we have here? So we talk about degrees. I have a little theorem. It's called hand shaking lemma that says let's see. Somewhere in here. Total degree that's the sum for all vertices of the degree of that vertex, right? That's what I mean by total degree. Take all the vertices, sum up their degrees. It's twice the number of edges. True or false? Of course it's true, right? I think you guys can prove that very easily. Can you? Look at the graph, any graph you like, and say, okay, what do you mean by total degree? What's the total degree here? 3 plus 2 plus 3 plus 2 plus 2 plus, we're not allowing loops, remember? Plus 2. That's the total degree. And what's the number of edges? 1, 2, 3, 4, 5, 6, 7. Did that sum is twice the 7? Why is that? Yes.
For every edge, there are 2 vertices connected to it, so it will increase the degree of each vertex by 1.
So you're thinking inductively, every edge adds a thing.
Mhm.
Right. Very good, but I would like a more like exactly what you said, but in more counting. I don't want to do induction. I want to count. So the proof that you guys gonna do at home is count incidence points. So by incident points, I mean look at the vertex. There's some edges coming out. This is an incident point. Wherever an edge connects to a vertex, that's an incident point. So I want to count these incident points. Here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. Right? Those are my incident points. Every time an edge connects to a vertex, that's an incident point. I want to count this in 2 ways. So that's how you're going to prove this at home. One way of counting is going to be the total degree. The other way of counting the same exact thing is going to be twice the number of edges. The proof is very simple. But I have questions here. How about the directed graph? Is that still true for directed graphs? You can think about that. And how does it work? A graph, by the way, a graph can be disconnected. Let's add that in here. Can be connected versus disconnected. Right? The graphs you've seen here are connected. Connected means for any 2 vertices, there is a path UV. Disconnected means here's a graph that has kind of 2 parts. So these are vertices, those are vertices. There's some edges, but there is no way to move from left to right. There's kind of a disconnect. So there's kind of two components, 2 connected components. This is connected, this subset of vertices. This is connected, this is a subset of vertices, but they're not connected to each other. That's a disconnected graph. A connected graph, like in here, is where I can reach from anywhere to anywhere. Doesn't matter how long it takes, how many edges are in the path, and so forth. The point is, it's reachable from anywhere to anywhere, it's connected. You think Facebook is a connected graph? Can I reach with friends from anybody to anybody? or it's a disconnected graph? Like there's some people who by friendship cannot reach to some other people. What do you think? All of it, all 2 billion people are connected to each other.
I think disconnected because there's got to be at least one account with no friends.
One account, what?
One account with no friends.
Right, excluding those. Like, this is the bot's account, they interfere in the election and all that. Right? Right. There's gotta be some community of 3 people just connected to themselves and nobody else. That will make a disconnected component. But here's a question. How, if I take Facebook graph and I eliminate small communities, that is people who only have 1 or 2 or 3 friends, up to K friends. I call that small. Everybody who has only up to K friends, kind of like out, doesn't count. What K do I need to choose so that the resulting graph is connected? If I'm only talking to, say, people of size, at least friendship size, at least 20, I'm excluding everyone with less than 20 friends. If I talk about people who have at least 20 friends, would I get a connected graph? Or would that K needs to be 30 or 50? What kind of K I need so that once I eliminate small components, I get the connected graph? This is the kind of problem that a company like Facebook or people who want to make money off Facebook are very concerned with, and it's a graph theory problem. Okay, well, so I'm counting on you guys to prove this because a lot of homeworks and final questions might be about handshaking lemma. Okay, and by the way, the problem that you had in the quiz, politicians shaking hands, is just another handshaking view of handshaking lemma, right? Let's actually talk a little bit about that sort of problem. That refers to the problem you had in the quiz. It's what's called a clique. Clique is a subset of vertices, call it C, included in V, such that any vertex in C is an edge. So a clique is a subset with all edges. So here's an example. This here is a clique. It has all the edges. But the other guys are not necessarily part of the clique. So A, B, C, D is a clique. Has all the possible edges in between. Now the graph itself is not a clique because there are some edges missing. If the whole graph is a clique, that's the problem you have in the quiz. All politicians shake hands with all politicians, then all the edges must be there. That's not a clique because there's some edges missing, but this subset of the vertices form a clique. And then let's talk a little bit about representation. So we say directed, undirected, degrees, handshaking lemma, edges. When I talk about here cycles, I want to add something. You tell me what does it mean? Acyclic graph. If I say acyclic, I mean what? No cycles. Right. Can have a cycle if it's acyclic. So directed, undirected, cyclic, acyclic, so on and so forth. You have to figure out what's an example of a cyclic graph, cyclic directed graph, acyclic directed graph, acyclic, undirected graph, so on and so forth. How about representation? Like for computer science, if I want to use a graph in my computer there, what can I do? You already had to do a little bit of this because you did, I think some of you did the one of honest problem 2 with graphs. So you have to implement somehow a graph if you use a graph, right? So here's an example of a graph. Say this is node 1, 2, 3, 4. And I can represent it with a matrix that is 1, 2, 3, 4. 1, 2, 3, 4. Of course, this UV here, this matrix M, matrix of UV equal 1 if there is edge UV is an edge, right? So since it's a simple graph, 1 to 1 is no edge, 2 to 2 is no edge, 3 to 3 is no edge, 4 to 4 is no edge. Simple graphs cannot have loops to themselves, so there's no edge in there. But for this graph, who's 1 connected to? 1 with 2, that's an edge, so that's a 1. It's an undirected graph, so if 1, 2 is an edge, 2, 1 must also be an edge. Where is 2, 1 in here? Right here, that's also an edge. So that's this edge. 1, 3 is an edge, 1. 3, 1 has to be also an edge. Again, in an undirected graph, if there's an edge that way, there's automatically an edge the other way. And then what else do I have? 2, 4, that's in here. And 4, 2, that's in here, right? And 4, 1, that's not connected. 2, 3, that is connected. Like that?
Yeah.
4, 2, that's not connected. It's like this, right? So I mark with 1s the edges that exist, and with 0s the edges that are not. If it's undirected, that means M is symmetric. This matrix have to be symmetric. This is an undirected graph. The other way to do this is with the adjacency list. Very often, adjacency list is much more useful in computer science than matrix. This matrix could be a very big matrix, including a lot of stuff I don't actually need. There's a lot of zeros in this matrix. In adjacency list, I'm only representing the edges that are there. So I have 1, 2, 3, and 4. Now, what are the points that have not reachable but direct edge with 1? Where can I go from 1? 2 and 3. This has not reachability. It's simply where 1 has the edges to. 2 and 3. 2 has edges to 1 and 3. 3 has edges to 1, 2, and 4. And 4 has edges to 4. This sometimes it's called dense because it's all the possible values, including a lot of zeros if you're missing a lot of edges. This sometimes is called sparse. Because see, the 0 edges, I don't do nothing for them. I'm only doing something when there is an edge.
Does that say undercut and M symmetric?
Undirected, sorry. Means the matrix is symmetric. Again, what I mean by that, if this is an undirected graph, this matrix is symmetric. How about if I put some edges here? Don't mess up what you just wrote. Draw it again. I'm lazy, so I'm not going to draw it again. Right? I'm going to say, okay, 1 goes to 3 that way, and 3 goes to 1 this way, and 1 goes to 2 this way, 2 goes to 3 that way, 3 goes to 4 this way, and 4 goes to 3 the other way. Now, this matrix is not symmetric anymore. Is there an edge from 1 to 2? Yes. How about from 2 to 1? No. That's a 0. Right. From 1 to 3? Yes. From 1 to 4? No. 2 to 1? No. 2 to 3? 2 to 2? No. 2 to 3? I have an edge 2 to 3 now? Yes. 2 to 4, no. Now 3 to 1. Is there an edge 3 to 1? Yes. 3 to 2? No. 3 to 1? 3 to 3, 0. 3 to 4? Yes. 4 to 1? No. 4 to 2? No. 43? Yes, because there is an edge 43, 4 to 4. So I change this to represent that. I can also change this. 1 goes to 2, and 1 still goes to 3. That's okay. 2 goes to 1. That's not good anymore. 1 is not in this list. 2 only goes to 3. All right? 3 goes to 1. Yes. 3 goes to 2. No. 3 goes to 4, and 4 only goes to 3. So I can make the necessary changes for directed graphs in both adjacency list representation or in the matrix representation to have now directed graphs as opposed to undirected graphs. Right? The last thing I want to do, we're going to do traversals next time. So traversals is next time. But the last thing I want to do about graphs is to talk about special graphs that are called trees. Trees are graphs undirected, connected, no cycles. Undirected, connected, no cycles. So how does that look? Is that a tree? Is it undirected, connected, no cycles? Yeah. How about I keep going from here? Is that still a tree? Yeah. Is that a tree? Why not? Like it says a cycle. How about if I have some other tree in here? Is that a tree now together? No, that's two trees. Two trees make a forest. Yeah. I think there was somewhere here. Of course, in a, yes.
So it's undivided. Go like from one row to the other, and then back.
Right.
So it's
So,
not a cycle.
no. A cycle, a simple cycle, you can use the same edge in the other direction.
Okay.
So, but you have a good point. I like the first point. She's saying in a tree there is a path between any U vertex to any V vertex. In a tree, from anywhere to anywhere, I have a path. So in here, I need to have a connection, right, to call it a tree. When I connect two trees together, I get a new tree, right? But I can't have more than one connection. If I have another connection, that's no good, because that's a cycle now. Is that true? For in a tree, there's a path from anywhere to anywhere? Yes, because it's a connected graph. Right? In a connected graph, there must be path from anywhere to anywhere. But here's something that you should prove. Theorem. In a tree, there is a path from anywhere to anywhere. But most importantly, the path is unique. In a tree, if you want to go from here to here, that path, the exact sequence of edges to go from there to there, there's exactly one path. It can be two paths. So that's an exercise. That's the thing with tree. But I can have another version of trees, which is rooted tree. See, in this tree, I didn't designate a node as a root. But if I do designate a node as a root, I say this one is the root. Now this becomes effectively directed. I won't call it directed, but effectively everything goes from the root. So now I have, here's, you know, is a tree with a root. In a rooted tree, I have levels or layers or depth. Root is 0. These guys are on level 1. All these guys are on level 2. All these guys are on level 3. That's level 4, so on and so forth. So if I designated a root, I have now who's on level 1? Everyone from the root. Who's on level 2? Everyone that's 2 hoops from the root, and so on and so forth.
Oh, yeah, I was just gonna sort of ask if a rooted tree is just a normal tree, but you could sort of rearrange it by folding it.
You can pick any node in a regular tree, make it a root. If I designate this one as a root, what level is this one?
Level 1.
1. Who's else at level 1? 1. Is this a level 1?
2.
No, that's 2. Who else is at level 2? 2. Is this 2? Who's at level 3? This one is the level 3, right? It's 4, 5, and right. Once I pick in a general tree a root, I can arrange the whole tree this way, just draw it differently, and I have clearly how far is everyone from the root, that's a level. And the one that's the farthest dictates the depth. The depth is how many layers we have there, other than the root. So I think that's enough for you guys to do the homework, I hope. And there'll be some notes if we miss something. There is something in the homework about bipartite trees and about traversal algorithms, which are very important, BFS and DFS. We're going to do those on Tuesday. So what I want to do now is to show you what you're going to have in the last honors problem. And this is going to require more. This is going to require more discussion. I want to show you this now to get you started, but I'm fully aware that you're going to have to think about this more. Yes. It doesn't. It's not online yet, but this is going to be the honors problem. I still have to formulate somehow what exactly you have to do. So, what we want to do is to replace the binary search tree from honors problem 4 with something else. It's still a sorting idea, right? That binary search tree, I'm sorting stuff, right? And I'm putting the stuff in the tree. And if the tree is balanced, we already talked about this, all the operations will be log n time. But when did the tree get out of balance? It gets out of balance depending on the input. Imagine the input is mostly sorted, or mostly sorted backwards. That could happen easily. And then the tree becomes a long list of things on one side. We want to avoid that. And I'm going to show you these linked lists that have that property. They don't depend, they can still go unbalanced, but not depending on the input, depending on your luck. So while there is a case for this list to still be unbalanced like a tree, then that case does not depend on the input. It depends on how you flip the coin, effectively. Actually, literally, how you flip the coin. So the trees have this disadvantage that while on average they're log n, there's a lot of inputs in nature that are not on purpose, but they are unfavorable to them. So then you can get out of balance. People have developed, by the way, ways to fix the balance of the tree. Red-black trees, big trees, so on and so forth, are algorithms to fix the balance of the tree to make it always balanced. In your algorithms course, perhaps you're going to talk about red-black trees. But here's a different data structure that that we're going to do. Imagine I have the skip list. That's the bottom. And we want that to be sorted. But every element is repeated multiple times. It has a stack. So this 9, it's listed once. Let me see, maybe there's a better drawing here. Hold on a second. This is the one I want because I have multiple processes. Here's the one. Sorry. Here's how this list look like. The bottom one, everybody knows what it is, right? A linked list, basic linked list. The trick in here is skip lists is that every element is stacked with itself several times. The stacking is extremely easy. It's a flipping a coin. I put a 31 here. I flip a coin. If I see a tail, I don't stack it. If I see a head, I stack it. And that's independent of the other elements. I look at the 31, flip a coin. If it comes heads, I put it again. And here I flip another coin. And I say, flip the coin. If I see heads, I put the 31 again. And if I flip the coin again, comes heads. As many, this when I flip this coin, how many heads I got in a row? How many? The 31 is given. Somebody give me 31. The bottom one doesn't count. It has to be there. I flip the coin, I get head, head, head. And the fourth time when I flip the coin, I got what? Tail. Because that's why I didn't stack it 4 times. Make sense? So how about how many heads I got here with this 15? 1. That's how I generate the stack. But then, at every layer, there's another linked list. So the basic linked list is on the bottom. But then whoever got stacked again, there's a layer 1, 2, links to the next one on that level. Happened to be 15. It could have been anyone else, right? And then there's another layer that says, Sophia, okay, we link to the next one that got stacked in there. So observe that this linked list here does not have these values effectively. From 2, I jump to whoever raised to that level. So I have multiple linked lists. So the question is, when I flip this coin, how high am I expected to go? Say a coin is 50-50. If you flip it, flip it, flip it, flip it. The highest number of flips, heads, 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 will be how many lists you have, right? My point is that you won't have that many. Because when you have a 50-50 chance, even if you do it for every element, I have n elements here. For every element, I flip that coin. The highest stack is not going to be more than log n. And that we need to prove. Right? So what I'm saying here is if I have 100 elements, for each of them I flip the coin until I see a tail, because this stack goes until I see a tail. In that case, even if I have many elements, it won't go the highest stack that much. So the number of lists here is logarithmic. If I have this structure, how do I operate with it? This is like a binary search tree, more or less. I go to the top list first, and I say, okay, go to the next element. If it's smaller, means you gotta go on the left side. If it's bigger, you gotta go on the right side. On the right side, how do I go on the right side at that level? I just move in the linked list, right? If I am to go higher, I just go to the next element in the list. How do I go lower? It says, okay, you hit it lower. What do you need to do to go on the left side? That's the new thing about skip list. Higher means advance in the same list, keep going. Lower means go to the next list under. So every time I see something lower, I'm going to go down one list. That, if you think about, that's exactly how binary search tree works. If you think of the left side being going down and the right side staying on the same list, this is effectively a binary search now. So that's going to require some time to think. There's some examples here. Okay, if I look for various elements, how does that work? Remember, every time I I have a value bigger than what I see, 31. I keep going on the same list. Every time I see a value that's smaller than the top of the list, I go into the next list. So the path of searching in this, you always start from there. It's going to be something like keep up, keep going until you see a smaller value, go in the smaller list, eventually go into another list, and another list, another list, until when I'm in this list here, of course I'm going to find a value. We need to prove that this search time is logarithmic. The way we prove that is to say the number of moves down, it's at most the number of lists, which we know is logarithmic. The number of moves sideways, we have to bound. We have to say, okay, how many times you move to the right as opposed to moving down. My point is, if we implement those lists, which you have to do for problem 5, the search is going to be logarithmic, like it was the binary search tree. The insertion and deletion easily is going to be like in the tree. If you have to manage an element, take it down, put it up, stuff. Flipping the coin, it's easy. What is the advantage of this versus the tree? So the tree, remember, goes bad on certain inputs. This can go bad only if the flipping of the coin didn't work properly. Suppose I flip my coin, every time I flip it, I get a tail. What that means in here? Every time I flip the coin, I get a tail. Nobody gets promoted up, so I end up with one list. But the chance of flipping the coin and getting a tail all the time, it's exponentially small, independent of the input. What's the chance of having too many lists? I flip my coin and I get heads 100 times, so I get 100 lists. That's a very small chance to flip a coin and get 100 lists on stack of each other. And it does not depend on the input. It has nothing to do with the values I've got. The trees can go bad depending on the actual input to my algorithm. That's why they can be problematic sometimes. So we need to, those notes we put online, and then Tuesday we're going to talk more about this problem.
Yeah, I want my own anyway.
There's a way that you feel about it.
We're trying to remove yes. Otherwise, you can do remove the first and add the second. I mean, I showed you the video, right?